Hello everyone, the title of this video is Finding the Center of Mass by Integration. This is part one of 3 different videos. And we are going to take a look at one-dimensional examples of objects. In other words, we're going to look at, our examples are going to be rods or lines of mass. And what we're going to do is try to find the center of mass location, starting with this first example where you have a rod of uniform density. Okay, so this could be like a meter stick, and really we don't need integration to find the center of mass for a meter stick, because if it's uniform, you could pretty much assume that the center of mass is right in the middle. But what I'm going to do here is walk you through the steps of how you could find it using integration and show you that you get that answer. That the center of mass is right in the center. So we already kind of know what the answer should be, but we're going to find it through integration. In examples 2 and 3, we'll look at cases that you are a little more difficult and you have to use integration. So this one is going to get you used to the technique. So first of all, the figure here shows a rod which has a length L. The rod is kind of laid down on a coordinate system. So the origin of the coordinates system is going to be at the left end of the rod. We're going to break this rod up into small chunks. So the chunks are the DMs. So I kind of highlighted one here. That's a little piece of the meter stick. And that piece has a certain mass associated with it that we're going to call dm. And we call it dm because it's a small piece. It's going to be calculus small. That little chunk also has a width associated with it, and we're going to make that dx. And again, that dx is going to be calculus small. And finally, the position of that particular element is going to be located a distance x from the origin. So x is going to be our locator vector, and that's going to take us to each chunk. And what we're going to end up doing is we're going to end up doing an integral where we let x go from 0 all the way out to the end of the rod. And we're going to find the center of mass that way. Okay, so first off, what we're going to start with is the formula for the center of mass that we came up with the other day for discrete objects, for separate masses. And we said that formula was a mass-weighted average for position. So we had to kind of add up the individual objects here and do a mass-weighted position and then divide by the total mass down here. So that formula is great as long as you have objects which are discrete, which are made up of parts. And in this case we have an object which is not discrete, but it's continuous. So we're going to replace that formula with an integral version. So instead of having mass, the summation of mi xi, we're going to do the integral of x dm. And instead of doing the summation of the individual masses, we're going to do an integral of dm. So we're replacing the summation with individual pieces with an integral that runs through all the different possible values. And that's the approach that we're going to take here. Okay. So before we jump into this, one of the things that you might wonder is how do you do an integral like this? You know, a dm integral. You know, how do you add those things up? How do you integrate it? And the answer is it's kind of tough, especially up here on top. And so we're going to have to put that into we're going to have to change that dm into something else, maybe a dx, and that will match our picture a little bit better. So let's state some assumptions here. We're going to assume that we have a uniform density. And we're going to express that density using a new symbol here called lambda, where lambda is going to be the mass of the entire rod, so just m, divided by its length. Okay, so lambda, if you think about this in terms of its units, is going to be something in grams per meter, right? And it's telling you something about how the mass is distributed along the length of this rod. Okay, so again, m here is the mass of the entire rod. I'll put that up here. And of course, L is the length of the rod. So if you divided mass by length, you would get this number. It's a lot like density in 3 dimensions, where you take mass divided by volume. Here we're doing it just in 1 dimension. And lambda, by the way, is the symbol that's oftentimes used for that. Maybe it's because lambda means L for a line. I'm not sure. So that's what we have. Okay. Now, if the rod is really of a uniform density, then that means something even more to us. Okay, so not only is the overall density expressed this way, but it should also be true that if you were to just look at a small piece of the rod, if you just looked at that little chunk in our picture, that the density of the mass should really be the same density that you have overall for the entire rod. So really this lambda, whatever value it has, it should also hold for the density at any small point in that rod. And so this is where the uniform part really comes in. The fact that it's uniform means that that lambda is going to be the same as that lambda. Okay, because no matter where you look, the density should be pretty much the same. And that is going to help us, okay, knowing this, because what we're going to do is we're going to rearrange it, and I am going to basically rearrange it so that I can get rid of the dm, and I can integrate instead over dx. So we're going to take this dm and we're going to plug it in up here on the top part, and we're going to do an integral in terms of dx instead of dm, because it makes a lot more sense to do that. Okay. So on the bottom part of this page, I'm going to scoot this up. We're going to really divide this into kind of 2 parts. Okay. On the top part, we're going to do the integral of x dm. That's kind of the numerator right here. Okay. And then on the other side, we're going to do just the integral of dm. And that's the denominator. And then when we're done, we're going to divide these 2 things, and we should have a center of mass, a position. Okay, so first of all, let's do our substitution then. Okay, so there's your dm, and we're now going to do an integral of x times lambda dx. Okay, and the reason that that's nice is because it's pretty clear from the picture that x is going to range from 0 all the way out to L. Okay, so x is kind of a geometry parameter. It's a position, right? So it's going to go from 0 to L. So I can put those endpoints, and now that integral kind of makes sense to me, that I can integrate from in between those points. The actual integral is easy, I think, I hope. Lambda is a constant, it comes out. And you're left with the integral of x dx from 0 to L. That, of course, is going to be 1/2 x squared times lambda. And then we evaluate from 0 to L. Okay, so then we'll just do the math on this. The 0 term goes away, and you end up with lambda times L squared over 2. So what we have here is that this integral basically works out to give us that. Now remember, that's just the top part of the integral, right? So we've only evaluated the top part here. And now we have to do the bottom part. And when we do that, maybe some things will cancel out, and we should get a simpler result. So for the bottom part, we do the substitution again. And for dm, we're going to do lambda times dx. and I'm going to integrate from 0 to L. And what I'm really doing here is just adding up all the mass in the rod. As I go from 0 to L, lambda dx would be basically just the little, the little chunk of mass, and I'm going to add those up all the way along the length. So then I can do that, and I'm going to get lambda dx from 0 to L. This, of course, is one of the world's simplest integrals, because the integral of 1 is just going to be x, and you can evaluate that, and of course that just comes out to be lambda times L. Now, a quick confirmation, right? Is that right? Well, if you kind of come back to what we set up here, right? The mass of this rod, if you rearrange, is just going to be equal to lambda times L. So that's good. So we actually, we didn't really need to do the integral, but I wanted to show you that you basically get a reasonable result here, which says that the total mass is equal to density times length. And that's nice to know. So, center of mass, what we do here, I guess we have to divide the top part by the bottom part. So my x center of mass is going to be equal to lambda times L squared over 2 divided by lambda times L. And wonderful things happen here, because of course your lambdas cancel out, and that means that the actual specific density of the rod doesn't make a difference. It just has to be uniform, that's all. We also lose the squared with that, and that leaves you with the answer that the center of mass of the rod of length L is exactly in the middle. And like I said, no big surprise, right? We knew that this would be the answer, but the point here is that we found it by going through a different procedure here. We use an integral to find it, okay? And we got the common sense result. So at this point, we'll stop the video, and what I'd like you to do is to give the next problem a try. In the next problem, the rod does not have a uniform density, but the density is going to change as you go further out. And of course, you're going to need to use calculus in that case. But the process and the steps are exactly the same. So do your best with that, and then when you're done, you can check out the video to check your work. Good luck.